So last time we saw the fundamental rule of counting, where if an first event or first experiment happens in n ways, the second in n ways, we simply multiply them for them to happen together. Multiplication rule is simply an extension of that, but it just involves probabilities. Suppose A and B are events, and we want to find the probability that A and B would occur simultaneously. The inverted U means A and B occurring simultaneously. Well, if B has nothing to do with A, or A has nothing to do with B, in other words, the occurrence of A does not change the probability of B, or vice versa, then we say A and B are independent of each other. So if we have independent events, then I could simply write it as probability of A multiplied by the probability of B. Good. So on any given day, a student has a 60% chance of going to Starbucks. What is the probability that a student goes to Starbucks on 4 randomly selected days? Of course, I'm going to assume, well, I'm not assuming, I've got to make sure that the student that I'm choosing is also chosen as random. Good. So I have 4 days. What is the probability that the student would go to Starbucks on the first day? 0.6. What is the probability that the student would go to Starbucks on the second day? 0.6. What is the probability that the student would go to Starbucks on the third day? What is the probability that the student would go to Starbucks on the fourth day? 0.6. Which is 0.6 raised to the 4th power, 0.0009. 1. 0.0009. You have to calculate. It might be 8 something, maybe even 7.
I got 0.1296.
When you multiply 0.6, oh, I'm dividing by, okay. I took this and I divided by 1, never mind, 0.1296. 0.6 that makes sense. So there is a 12% chance, approximately, guessing, you can say that retain 4 decimals. So anytime you have a probability, keep 4 decimals. Don't round it to the next 10th place. Don't round it to the next whole number. What is the next whole number? The nearest whole number. 0. Can I put the answer as 0? Absolutely not. So 4 decimals or more is correct. So 13% chance approximately to be very perfect or precise, 12.96% chance that the student will go to Starbucks on 4 randomly selected dates. So here is my question. Do you believe that these days are independent of each other? According to the construct of the problem?
Yes,
Why? Tell me.
because it doesn't matter if day 1, if the student goes to Starbucks, it won't affect whether or not he goes on the rest of the day.
Very good. So no matter what day you pick, I've made a statement that whatever day you pick, there's a 60% chance that the student would go to Starbucks. So it really doesn't matter what this day is. You always have that 60% chance. So I have 4 events: going to Starbucks on day 1, going to Starbucks on day 2, going to Starbucks on day 3, going to Starbucks on day 4. All of them are independent of each other. So what did I do to the probabilities? I simply multiply them. That's what this formula means. Good. So if A and B are independent events, if we want to find the probability that they would happen together, we simply multiply their individual probabilities. Are we clear? Then comes the case of dependent events. If I have 2 events, A and B, there are 2 possibilities. Either A could depend on B, or B could depend on A. If I want to find the probability that A and B would happen together, and I'm giving the fact that A depends on B, which event should have occurred first, A or B? B. So the process is the same. I'm going to write probability of B first, multiplied. This is the part where you might have confusion, but don't get confused. It's not that difficult. So we write it as a notation A vertical dash B. This simply means A is happening next, given the fact B already happened. Does that make sense? So A vertical dash B simply means A given B. A conditioned on B. So we are simply saying that B had already occurred and the probability of A, which happens after B, is determined by B because it happened already. Does that make sense? Yes? If A has nothing to do with B, I'll simply write it that way, correct? A's got nothing to do with B. In other words, A and B are independent. This formula ends up being that one. Yes. Now, if we switch, and if B depends on A, how will that formula change?
Switch the letters.
Switch what, Talon?
The letters.
Switch the letters, that's it. So here, B vertical dash A simply means, take a guess. That's true, but what does B vertical dash A? What does it mean?
B and that.
B comes after.
B given A. Or
B can't happen without it, or B condition.
B is conditioned on A. You're right, Sue. The easiest field of statistics, frequentist approach, that we are going to do in this class, will assume that events are independent of each other. Now, this comes in a different methodology, different field of statistics, called Bayesian statistics, where you often look at dependent events. They commonly show up in medicine. One good example, let's say I'm going to take two events, diabetes and gender. Do you think the risk of diabetes would depend on gender? Okay, diabetes and obesity. So there is a correlation with gender also. So gender could be a factor. So diabetes would depend on, race, obesity, gender, whole bunch of other things. So I can't simply do a problem that, okay, what are the chances diabetes happens in 5 different people of different races, different genders? Does that make sense? Because there is dependence and I've got to account for that dependence. Often this shows up in medicine, but we use it in other fields also. But at the end of the day, I'm simply multiplying the probability of that event with the probability of that. I'm not dividing, that doesn't mean divide. It simply means probability of A given B. That's it. Y given B, B had already happened. Good. Now, those two have a name. The race. Very ingenious in naming this. Any thoughts as to why we call them conditional probabilities? Literally, we are conditioning A with respect to B, B with respect to A. So they're called conditional probabilities. let's start with that. Let's say I have a basket of KFC. Like, what do we like? Drumsticks, wings, breast. Wings, okay. 2 wings, 8 breasts, and 4 thighs. Good. Total, how many do I have? 14 pieces. Correct. Okay. I'm extremely hungry this Monday. So, sure, you may say, if I close my eyes and grab one piece, that piece is, you will know what it feels like, right? There is no randomness. So you're magically asking some genie, the genie is going to throw a piece of chicken at you at random. Good? Good, in your face. So you want a piece of chicken, so you're asking the genie, so the genie is grabbing and throwing a piece. You wanted a breast. What is the probability that you would get a breast? 8 out of 14. How did you get that, Rebecca?
There's 8 of them and there's 14.
8 of them, 8 breasts divided by the total, 14. You can reduce this later, but and I love to eat. So I ate that within the last 5 minutes. So I asked my genie again, give me a piece of chicken. So genie throws another one. This time I would like to have a thigh piece. What is the probability that I would get a thigh piece? 4 over 13. Why is that, Grant? Can you hear him? You can't? Wow. What did you say, Graham? I can't hear you.
Sorry, you ate one chicken breast, so it's -1.
Right, so I ate one already, so the box, the total reduces, so all the genie has is 13 pieces to select from. If I have to write it as a formula, and if I want to know what are the chances that the genie gave me a breast piece and a chicken piece simultaneously, I would like to know what are the chances that it would happen. Well, in terms of the notation, I could write it as probability of breast multiplied by the probability that I would get a thigh piece, given the fact that the genie threw me a breast piece. Now, do you see conditional probabilities? Now, this would be event A, event B, event A. So the second piece, whatever that might be, depends on the first. If I am a glutton and I kept on eating and I kept begging for more food, what are the chances that I could get 20 pieces of chicken on that specific day? What is that? 0. It cannot happen. Eventually, this probability will decrease. That box is going to keep on decreasing in count, so I'll get 0. But do we understand conditional probabilities? Now, in practice, we just don't have to. We could have hundreds of events. Conditional events. That is without replacement. Without replacement resulted in dependent events. Do you agree? The second event depended on or depends on the first. Same scenario. So this time, let's say I'm hungry and I want, I could smell KFC, but unfortunately I'm allergic to chicken. So I'm craving KFC, so I asked the genie, well, throw me a piece of chicken. But since I can't eat it, I just grab it, take a whiff, and give it back to the kid. Good with me. In other words, I'm gonna throw it back, the genie puts it back in the box. What is the probability that I would get a breast piece? Very first time. Still 8 out of 14. I'm allergic to chicken, so I take a breath or two, throw it back to the genie, but this time I would like to have a 5 piece. So what is the probability that I would get? 4 out of 14. The second time, this piece did not depend on what I got the first time, correct? So here we have independent events. In other words, we are simply multiplying probability of A with the probability of B. Now, I can keep on repeating this process until I'm completely satisfied. Yes, I could say, what is the probability that I try this 20 times? It'll have a good amount of probability because it is not going to become 0. But do we understand the connection between replacement and dependence? So most of the stuff, theoretical stuff that we do in this class falls under replacement strategy. Can I erase? Yes.
Why would the probability be 4 out of 13 for the 5?
So initially there was 14. So 8 breast pieces, 8 out of 14. Do you understand that part? So the moment the genie throws it at me, I ate that entire breast. So what happened to the total here?
Oh, okay.
It went down. So this is problem 7 and 3.2. So I've started with this table just by the way I've illustrated here. Could you say that I'm trying to establish some sort of a connection between gender and whether they got a business degree or not? Yes. So I'm sort of assuming dependence or assuming independence. But I can't just make up, looking at this table and say, oh yeah, they're related to each other. There has to be, a very scientific way to do it. That's where the probability comes from. Here we're just going to find the probabilities. We're not going to determine if they are dependent or independent yet. So we want to find probability that a person is male, given that the person had a business degree. Good. So if I define this to be event A and that as event B, you go back to our formula. Good. That is our formula. In this problem, though, we have to find probability of A given B. In other words, we need to find this conditional probability. How do we do that? Algebra. So, probability of A given B is simply the probability of A and B divided by the probability of B. If we switch things around, of course, we can change the letters. Since we have A and B, there is a name for that probability. It's called joint. Probability. The denominator is by itself, and in this setting, we call that marginal probability. I will explain as to why they get those names. Don't have to memorize them at This table that I created is what we call a two-way table or a contingency table. So this is a contingency table that relates whether a person got business, non-business degrees versus their gender. So if I use that formula, I would like to find the probability that a person is male and got a business degree divided by the probability of someone having a business degree. Do you agree? A, B divides by B. Great. Male, the probability that someone is male and they have a business degree, what is the value? How do we find that probability? How many of them all is a male and has a business degree on the table? Right here, this and that. So that is our number. And what is our total? No. 163
363.
divided by the total.
1.8 million.
What is the total?
894,935.
With respect to the entire population, how many of them are male and have a business degree? Call the total and we'll get to your number soon. Divided by business, what is the probability that someone would have a business degree? Divided by, yes.
Why would you divide by the total with the inclusion of business?
Well, that's what I'll explain this second. So divided by the total number, which should be 1,894,934. Yes. If you flip and multiply, you would get 199,310 divided by 363,799. Good. Again, algebra, I'm not going to get into how to do this. You should know this by now. So the final probability is 191,310 divided by that. What is the decimal value? 0.54.
Yes.
53. Exactly.
No, around 0.525.
One more decimal.
8.
So 52.58%. Great. Now, why should we divide by the entire population? I'm asking a question of all the people that I have sampled, how many of them are male and have a business degree? Yes. So I'm going to divide it by the total. Of all the people that I have sampled, I would like to know the number of people who hold a business degree. So I take the total of business people and divide it by the total number of people that I sampled. Does that make sense? Which is why I divide by that. What is her name? Lauren? Elizabeth?
Lindsay.
Lindsay, did you follow as to what we're dividing by the total? Okay. Now, the reason why we call the denominator as a margin of probability, because this is a table, those are the margins, hence the name margin of probability, right? I could have gotten this answer a different way. That's what Jules mentioned earlier, even before I did this, she gave me the answer. I did it this way to demonstrate multiplication rule, how we apply the rule. In this problem, things are obvious to you. Other problems, you will need this rule, which is why I did it this way. But if we think carefully, what is the problem asking us? Probability that someone is male, given the person has a business degree. Yes? So I'm conditioning on the fact that people must have a business degree, correct? How many have a business degree? So my condition total would be this, yes? Out of that amount, how many of them are male? That's the answer. Does that make sense? So once again, this table, I did it this way because the table makes it easier for you to recognize the answer. But there are some problems where you have to go through this process to get to the final answer. Does that make sense? Yes.
If we have to go to the
We know the formula, probability of A given B is the probability of A and B divided by probability of B. In our case, we want to find the probability that a person has a non-business degree and female. Non-business and female would be that amount. I'm looking at the entire population, so the entire sample size. So I'm going to divide it by the total. And the probability that a person is female in the sample. That would be that amount divided by the total. If you flip and multiply, the totals will get cancelled. So the answer would be this divided by that. And what do you get?
0.84.
Exactly.
0.
0, 0. What else?
8406.
8406. Okay, thank you. So you can do this directly. Since it says non-business degree given female, I'm going to condition on this total, which is 1,082,265. That will be the denominator. Out of that total, how many of them have a non-business degree? That's about right. Good. So do understand the process.